Okay, so by the way, what class is this one? 9. Okay, so in this lecture, we're gonna take a few steps back, and that's why there's not gonna be any recaps. We're gonna discuss the energy momentum tensor in CFTs. Namely, we discussed back at lecture 2, I guess, the conformal transformations, computer that generates in the algebra, but we did not discuss the conserved currents. Okay, you have two more symmetries in your theory, namely scaling symmetry and special conformal transformations symmetry. And we're going to discuss what are the conserved currents. Actually, just for the scaling currents, the special conformal currents I can't state the results, but all the interesting physics is on the scaling currents. Okay, we come to understand this. Okay, so basically then what we're going to do this lecture. Can you read this?
Black one is pretty.
Yeah, it's not that good. So it's just a statement that just to every continuous symmetry in your action, there will be a conserved current associated with it, okay? And the conserved charge. I'm not gonna rederive another theorem. Okay, I'm just gonna state the results for continuous space-time symmetries. Okay, the conserved current will be J mu. And in general, it's going to have this form for any continuous space-time symmetry. This capital phi means any field in the any spin. It could be scalars, fermions, gauge fields, doesn't matter. We have I'm going to call this delta. Okay, so what is this current? This is what comes from, say, you're going to do space-time transformation. Infinitesimally has this form, okay? And generically, this epsilon can depend on x, okay? And this will be the associated conserved current. Okay, Aula, of course, the Lagrangian, but you can have two different kinds of contribution in this functional form. The first one is this one parenthesis, which comes from the variation of space-time itself. Okay, and that's why I call it delta I. This I stands for internal. This is the variation that is induced in the field space from this space-time variation, okay? So for example, if you do a rotation for a scalar, this guy is 0, but for any spinning field, you're gonna have the generators of the SOT, okay? So this purely space-time, this is from the internal part, okay?
From indices, sorry. So
yeah,
this is
the indices, okay. I wrote wrong here too. Okay, so in general, what's going to be here is say since I call this internal, I'll call this I guess some people call B for base space-time. Okay, and here just going to be in general this parameter. The point is that now everything is correct. The point is that, of course, this translation, this infinitesimal translation can actually be for actual translations. You're going to have 4 possible translations of the time and the 3 space directions. For rotation, you have 6 possible rotations. For scaling, you only have 1. Okay, so this translation can have the parameter that characterizes a specific transformation can have additional indices here. And what I've done is just mixed. Okay, yeah, thanks for that. And this guy in parentheses here is what we usually call the. Okay, no, just one step. Let's do this for translations. Okay. The transformation is then some constant translation. Okay, in right. So for translations, this first off, this internal, no matter the field to take, this vanishes for translation. Okay. You can recall, maybe it's good to recall this. What I write here. We saw that the translation generator acting on any field, capital Phi, has this effect, okay, which depends on space-time. Okay, it goes to the derivative. For rotations, we had going to abbreviate like this, the orbital angular momentum, just like x nu, the nu minus x nu, the mu. But we can also have a spin part here, okay? And this is the internal transformation for rotations. For scalings, we had, there was a minus I here, x dot x mu, the mu, plus the scaling dimension, okay? So scaling still will have an internal transformation, okay? This second term here does not depend on space-time, okay? And everything here will depend on space-time. Everything here went with a factor of x, okay? But we won't worry too much about the special performance transformations. Okay, so for translations then, the internal, there is no transformation in field space induced by constant translations. And the variation from the field from this, what I call dB, is just a Taylor expansion. Okay, this is by definition. Just recall this is the same field. Okay, since there's no transformation, internal transformation. I compare different infinitesimally closed space endpoints. Okay, so you just expand this, and what you're obtaining is just your constant mu, your parameter, mu by x. Okay? It's not Taylor expansion. And so, plug these two guys here. Your epsilon mu is a mu, which is a constant. dB, delta B is this, delta I vanishes. So, and then what I told you, this parameter in this case is a 4 vector too. Okay, so you have a conserved current that will have actually this new index nu here because of the first term. Okay, you have the Lagrangian. And okay, this mu index is the one that appears here. Okay. Now here we have to insert this this result. Okay, so we have to use another index, which I'll just call a bit up front here, nu. And we're gonna have the nu 5. So your current for translation is actually a 2 tensor. Okay. And this contribution here is just going to be mu. Mu L, okay?
No, I mean this is a dead index, no, the sum of values, no, this is
I'm just getting a bit ahead of myself. Every single step here. Okay, you must. What we do now is this parameter is arbitrary, so you can just then when you just substitute this for just write this as a new delta mu, okay, and then you retain what I had originally written here. Okay, and this is what we call the canonical energy momentum tensor. Okay, this is the energy momentum tensor that we compute from the series. Okay, and the other consequence from the series that this is a conserved current. Okay, so from the fact that this current is conserved for translations implies that the canonical energy momentum tensor is also conserved. Okay? And just for completeness, for rotations, I'm not gonna rewrite it here unless somebody wants it. Okay. But the result is I hope I have it. Where did I write this? Okay, no, that's actually derived because it has an internal part. Okay. Because this will be the subject here. For rotations, we have our transform. Space-time point is just this, okay, where of course this is anti-symmetric. Okay, just parameterizing rotations, and we identify that this will be your epsilon mu that enters here. It's going to be this. Okay. And we see now that it does depend on x. Okay, so it is a bit more involved, but if you play the same game, what you find is, and okay, I'm already dropping the parameter after all the index definitions. So for rotations, we end up with a conserved current that has 3 indexes. Okay. Just for translations, we had one more index inside the mu. For rotations, we had 2 indexes, so we end up with the 3 tensors. Okay? And the result is just the conserved canonical momentum tensor. Let's go. Okay, this is what comes from this part. Okay, from space-time variations alone, and you can see this is just angular momentum, basically. And we have an internal part. Okay, if your field is a scalar, then it stops here, of course, because the one has a spin 0. But in general, you have a contribution here. This capital sigma, of course, are the generators, okay? Okay, so this is alright, so this is the conserved current associated to rotations. Everyone has seen this. What does the imply for this current. But recall that when it is a conserved current with respect to this in this convention to this the first index, okay, which is the one that is coming from the beginning here, okay, not the nu or the rho. And okay, so when this derivative hits this canonical energy moment tensor, it vanishes, okay, from translational symmetry. And when it hits x, you're going to end up with delta rho nu. Same thing here, when the derivative hits the energy moment tensor, it vanishes, so delta integration comes from the x nu. And we have this and addition. Okay, now nu becomes rho, and here nu becomes nu. Okay. And just for convenience, I'm gonna call all this with the factor of I included. So, we're gonna call all of this sigma mu nu rho. Okay, just for short. Okay, and this is a conserved current, okay, from null to zero. So this must be zero. Okay, so what do we see here? We see that if we had the scalar field, this guy vanishes, okay, and the energy momentum tensor is symmetric. This is the canonical, sorry. Okay. The canonical energy momentum is symmetric. If your field, if you have at least one field that is not a scalar, your canonical energy momentum tensor won't be symmetric. Okay. Then just recall that there are billions of definitions of energy momentum tensor. The canonical energy momentum tensor is again by definition the energy momentum tensor that arises as a consequence of translation symmetry by applying the theorem. Okay? But this is usually not desired. You usually want your energy momentum tensor to be symmetric because maybe the strongest reason is that if you calculate gravity, the source of gravity is a symmetric energy momentum tensor. Okay? So how do you reconcile those things? There's this thing that some of you might have heard already. There is this Bell-Infante improvement of the energy momentum tensor. Okay, it basically is you take a non-symmetric canonical energy momentum tensor and you modify it. You add some term to it, such that you do not spoil the conservation. Okay, but you do end up with a symmetric energy momentum tensor. Okay, and let me see. I'm just gonna give you the result for now.
You sum usually a derivative of an antisymmetric tensor, right?
Yeah, because I'm just gonna call this improved energy moment tensor. I'm just gonna call it all the C. Okay, it is usually the canonical one plus. Usually write it this way, and people usually call it E for Bell-Infante. Okay, with you require that this tensor be antisymmetric in the first two indexes, because then you're guaranteed that you won't spoil the conservation. Okay, because then if you apply the nu here, you're going to have the nu the lambda, but since it is antisymmetric, this vanishes identically. Okay, so you do not spoil the conservation, and you can further prove that the conserved charges, namely energy and momentum, and angular momentum here for the rotation eventually, are the same. Okay, they interpret the same, obtain the same result. So physically, regarding everything that you can measure from the energy momentum tensor, nothing changes. Okay, but you successfully symmetrize it. Okay. The specific form of the Bell-Infante tensor, I have it here, but just gonna And I'm gonna hand it out to you right now. Okay. I'm gonna compute it. Kind of compute it in a moment. So are there any questions by this? This should be kind of familiar. I guess everybody saw something about this at some point. Okay. The news is going to be for the scaling current because again the scaling current will be more involved because they have an internal part. Just see here that what spoils the symmetry, the canonical influence tensor is precisely the internal part coming from speed. Okay. So naturally the manifolded improvement, the manifolded tensor, I guess discrete tensor is usually called manifolded Rosenfeld, and manifolded tensor is the energy momentum tensor. I might be use some wrong terminology. I don't remember. Okay, you have a question?
No, it was just, I mean, if I look at these two equations, it looks like you can always choose the exactly one, maybe that's what I said, like the signal which is operating on the internal degree of freedom, no? Is it? Because this should also be anti-symmetric probably in the second.
In the first two indexes.
No, I like if you just, I mean,
B is a combination of sigmas.
okay, but it's not exactly that you can use exactly V equals to minus sigma?
No.
No? Why?
It's a combination.
Okay, so sigma is not anti-symmetric?
Sigma is anti-symmetric. Okay, no. This sigma is anti-symmetric in Lulu. Okay? These two indexes here.
Yeah, so why can't I use them? Just yes.
Because you need it to be anti-symmetric involving this mu index, which comes from the theorem.
So
and
it's
this is not the ones up here, so we must do a linear combination. Okay? It is actually a simple expression. We're going to compute it here, but maybe I should do it now. Since we're talking about it. Let me just. This room is not. Sorry. We got the first result. Okay. Let me just state the analogous problem to the scaling current, and then we're going to go back to this to study the improvements itself. Okay? So, any questions? Well, we're going to keep this on the left.
Could you not raise down the rotations then?
Okay, just outside here. Okay, for scalings. We have x mu equals the region of x mu plus lambda x mu. Okay, and now notice that your parameter is just lambda. Okay, and your epsilon mu is this guy here. And again, it depends on x. Your internal part, the transformation, in the internal space is just think about this delta here. Basically. I guess by convention we drop the I there, so maybe I should drop this I. Maybe I miss a factor of plus or minus time. Okay, they're just conventions. Okay, so the variation in internal space is just basically given by the scaling dimension of the field. Okay, and the variation base space. We're talking about that. Basically, it is not that. In principle, I should. Let's just pretend I already ripped off the parameter. Okay. And it is. Okay. Just to read. Oh, no, sorry. the rotation has design because you have one eye here, but in the spinning matrix it does not have an eye. Okay. So we have this relative axis that should appear at an eye. So at most I missed a minus sign, but the eye is correct. So you just again plug this epsilon mu delta I delta b here in this general formula, and what you obtain is observed current. This time indeed for just one index because we only have one parameter, so one constant current. And the result ultimately is again your canonical energy momentum tensor. It always appears because of this. Okay? You always have this structure that gives rise to the canonical energy momentum tensor. Contracted with x nu coming from here, and an internal part, which is maybe I just everyone is under this scalar dimension right now, not some sort of variation, and that's it. Can everybody see this? It's pretty straightforward. So now the question is, what does the conservation of this current implies on this side? And then again, when the time hits the canonical energy momentum tensor, it vanishes because I also have conservation. So we have where you get is the trace of the canonical energy momentum tensor, right? We're gonna get delta nu mu, and again another contribution. Okay, and of course this is 0 because it is another current. So what we see here is again that we have in general an internal part here that spoils the nice property of tracelessness of the canonical energy momentum tensor. Okay. So if this term would not be present, then your canonical energy momentum tensor would be traceless. So this is an analysis to what's happened here with rotations. Okay, we had an internal part that spoiled asymmetric, or the possibility of having asymmetric canonical energy momentum tensor. And here we have an internal part that spoils the possibility to have a traceless canonical energy momentum tensor. And so the question is, can we play a similar game to this Bellin-Fante improvement here, so as to define another improved energy momentum tensor that is indeed traceless? Okay, so that is the question. Okay, and just one point before we actually study this question, the resolution of this question. This question is actually more important than it might appear at first sight. Can I erase this? Can I erase this? The reason is the tracelessness of the energy momentum tensor is actually connected to the question of whether or not scaling symmetry implies full conformal symmetry. Okay? And that's what I'm going to explain now. And the trick is if you do recall that how did I put this? Recall that if you can bypass this Bellin-Fante procedure here and already obtain a symmetric energy momentum tensor if you do the trick to coupling the theory to gravity and perturbing the metric. Then the asymmetric conserved energy momentum tensor arises as a response to this perturbation. Okay, this is a widespread trick. So the general expression you get is this. Okay? In these space-time dimensions, you usually have a square root minus g to make this a measure invariant. You usually have one expression like this, okay? Everyone has seen this, right? Everyone has seen this, okay? This procedure usually already furnishes you a conserved symmetric energy momentum tensor. So, recall that from lecture, either the first or the second lecture, we computed that this quantity for a general conformal transformation, okay? And the result was in general ng here, and the divergence of the parameter, okay? Usually, we're interested in conformally flat field theory, so this is just going to be flat, okay? Where these epsilons, of course, any of these epsilons here that we may consider, okay? So when you see these two disappear, you see that the derivation of the action to any conformal transformation is this two cancels. You can plot the factor of 1 over d at front here, and something like this. Okay, this delta will hit the energy tensor to produce its trace, and then we have here the divergence. Okay, so this is for any conformal transformation. Okay, so we have to be just careful with one thing here. If we do have a traceless energy momentum tensor, we have, then this vanishes, and we have conformal invariance, the full conformal invariance, the full conformal group. Okay, but the other way is not true. Okay, if this side vanishes, if you can compute this explicitly through any other method, it does not mean that the energy momentum tensor is traceless, because we just specialize to a particular kind of transformation here. This is not a general transformation. And you can see it, this sounds a bit strange to you. Just take, say, translations, okay? Translations and vanishing divergence because these guys are constant, okay? So if you have a theory that you only have translation symmetry, not even rotational symmetry. If you do this computation, you can see the action vanishes, but it does not vanish because the energy momentum tensor is traceless. It vanishes because this divergence vanishes. And the same thing happens for if you take the rotations. This will vanish because this is a curve, okay? The divergence of a curve is 0 again, okay? So for the usual Poincaré transformations, this would vanish not because the energy momentum tensor is traceless, but because this divergence vanishes, okay? So there's just this subtlety, okay? And it is usually some topic of confusion. But suppose, so just to illustrate, if we did take scaling transformations, the parameter then would just lambda rho. So we would obtain basically lambda times d, okay? And this d cancels, lambda is just a positive, not a zero parameter. So the only possibility is that if this is to be a symmetry, the only possibility is that the energy momentum tensor is traceless. Okay. The integral would still be the integral itself would still be 0. If this would be total divergence, then yes. But that is a point. Are there any questions about this? I hope this is clear. Okay. Conformal invariance does not imply that your energy momentum tensor is automatically traceless, but the other way is true. If you have a traceless energy momentum tensor, then you have well, it is one of the requirements for full conformal symmetry. Okay, all this discussion as it is now is classical. Okay, I'm not computing any correlates. I'm not using any path integrals or anything like that. Okay, if you want to ask the same questions in the quantum realm, then you have to go through this stage, but you would also have to worry about anomalies and things like that. Okay, for now, we're gonna discuss the order later this class. But for now, the discussion is entirely classical. And just try to understand the classical problem of whether or not, when does scaling symmetry implies conformal symmetry. Okay. And having discussed that, let's go back into the improvement business. Are there any questions? Yes, I can erase this now. Any erases? So when we do an improvement of the canonical arrangement momentum tensor, either to make it symmetric or traceless, we do not want to spoil the conservation. Okay? And so we have this condition that is a consequence of translational symmetry. Okay. And we want to add terms to the arrangement tensor, but we want to keep this conservation on. Okay. And just as I anticipated that, the usual way to do this is to add a tree tensor that has this form. Okay. Introduce this tensor here, such that it is antisymmetric in the first few instances. Okay. This will ensure that we maintain that we still have a conserved energy momentum. Okay. But as it turns out, like in hindsight, some people did the computations and they realized it is easier to, instead of adding a term like this.
But wasn't that just for rotations?
Whether or not we want to make it symmetric or traceless, we do not want to spoil this. Okay. And the way to do this is just to add a term like this. Okay, if you only want to make it symmetric, then it will be the Benefante tensor. Okay, there will be a combination of the spin generators. But if you also want to make it traceless, it's going to be something else. But in general, it will have this form. Okay. Maybe I should use, and in fact I use another letter.
But in case
here I call it F.
But for translation of symmetry, do we need that or not?
Translational symmetry? No.
No. Okay, so
If you only have translational symmetry, you do not have rotational scaling or nothing else, then this suffices. Okay?
Okay.
This is the only symmetry we have, this is the only conservation law we have.
So in other cases we need either the Benefante tensor or this tensor, or maybe even both.
Yeah, this is a generic. Okay, this is
Okay.
a generic improved tensor. If you only want to make it symmetric, then this F would be the B from the infant and so on, but in general, they're going to be something else. Okay? This is just the general solution if you want of improving the canonical arrangement tensor, but keeping its conservation. Okay? Any more questions? Okay. So the point is that it is usually instead of writing it like this, introduce another free tensor and write this improvement like this. It's just a choice. It makes it easier to, at least in the case for the infante, it makes it easier to identify who this guy should be. Okay. Where this guy is anti-symmetric in the last index. The 2 and the 3 index. Okay. F was anti-symmetric in the first 2. This tau is anti-symmetric in the last 2. Okay. And this linear combination is you can go back and forth between F and tau. So F is just F is just this. And you can have a similar expression for tau in terms of F. Okay, it's just a choice. Okay? It makes the basis of reading reading this guy off is easier than reading this guy off immediately. Okay.
What's now?
It's just another pretense. Okay. Just a redefinition. Just because some people did this computation, and so that instead if you started from here, instead from here would be easier. It doesn't matter much actually. But so what we must do here is identify the tau. Okay. So let's do this for rotation, and we will recover the Benefante tensor. Okay, the Benefante and Benefante tensor. So again for rotations. So we're doing this because we want a symmetric energy momentum tensor. Okay, so it means that we want this property. This is for the improvement. Okay. By using this definition, I raise the index, the new index. If I take temu nu minus n nu, and I want this to vanish because I want to be symmetric. That's the whole point of doing this. Then this right hand side becomes the difference from the canonical energy momentum tensor plus something else that comes from here. Okay, and due to this, you can check later if you want. Due to this symmetry, due to this anti-symmetry in the last 2 indexes, all that survives is this term. Okay, and this should be 0. I just took this equation and I broke it into two parts. And okay, no, that's fine. Okay. So this is say this. This is the first point. Okay. Now comes the second point. Okay. Conservation of the conservation of this current that arises from rotational symmetry again implies what I call okay. This is just the relation that I have written over there already erased. Okay. This, the first point comes from manipulating this equation. This second point is just the conservation law. Okay. And when I substitute this in here, okay, I use this equation, the Miller's conservation law, to write this guy in terms of the conserved current and this internal part. Okay, and substitute it here. So guy is just a constant current. Minus this one. And this one that was already there. Okay. Was it too confusing or? I don't know. Okay.
I'm just confused. Shouldn't equation 2 be equals to 0 for the current we conserve?
This?
Yes.
Yeah, it is 0.
It is 0.
Yeah, but I'm just not using this fact.
Huh?
I'm just not using this fact.
Okay, you don't?
Okay, that would be a 0 here, but I'm using this side.
Yeah. Okay. Just, okay. Yeah.
Okay. I could have used the other side too, but wait, would lead to the same thing. I just want to isolate this combination here because I want to get rid of this one here. Okay. That's what I've done here. I brought this guy over here, and then said that this equals the difference between this guy and this guy. We substituted it up here.
Yeah, okay, this, because otherwise we'll just get that what you substitute would be minus divergence of lambda that's the same. Okay. Yeah.
Oh, okay. It doesn't matter. We're not understanding. Well, the point is, then combine everything together. Okay, remember these were the same equation basically. Okay? We'll do two sides. Of this equation here. Okay, so I'm going to combine this with this. Okay. Well, what I've done here, I got rid of the canonical energy momentum tensor that is not symmetrical. Okay, and now I have an expression for the improved tensor. Okay, coming from this side. And we have this. Okay. Just recall, this J is the current that arises by applying the theorem with for rotations. Okay. And so this is conserved, basically.
So why do we write as
Yeah, I don't know. So this is conserved, basically. And if this tensor, this improved energy momentum tensor, is to be conserved, then this must cancel each other. Okay? Remember, when we did this and found the canonical energy momentum tensor, we only had this. Okay? We had the internal part that spoiled the symmetry of the energy moment of the canonical energy momentum tensor. But now the effect of writing, adding this term here is to produce this extra contribution here. Okay? If we start with the F, then we will obtain 3 F's here. Right? So in the rotations, for the rotations, it is easy. You can simply read that. You can read that the tensor we after is this one. And just recall that I defined this sigma with 3 indexes to be as a factor of y. Where again the sigma with only 2 indexes is just the spin matrices, okay, for the appropriate representation. Okay, so the Belly function improved the energy, and the Belly function energy momentum tensor is just the canonical energy momentum tensor, okay, plus a combination of these guys here. Okay. That's it. And the interpretation is that you have to take this would be kind of a bound current, okay? Bound spin current arises from the intrinsic property of matter. Okay. So when you properly take this into account in your animal tensor, then that is something symmetric. Okay? It has some physical interpretation. And are there any questions about this? Okay. It's okay. And now the question is, when we do the same thing for scales, okay, we would write something like this and play a similar game here, but with the scale transformation, and try and see if we can solve for tau. Okay. And the point is, the reason I did for rotation because I don't want to do for scale is because it is too big, but you have to solve some differential equations. In fact, the identification is not as immediate as this one. So I'm gonna do to some points, I guess, but eventually I'll just give you the answer. It's okay. Let me see. Scales. What we will discuss to a certain extent is when we can successfully do this for scaling symmetries. So for scalings, we had always erase it because I was used. Okay, so the property we want is that the improved arithmetic tensor to be traceless. Okay. What we got for the canonical arithmetic tensor was this. Sorry, we want it to be traceless, so tracing out this equation, basically. We will use this thing I'm writing here, which is okay. And again, remember that it is antisymmetric, it has two indexes, so this contraction vanishes identically, it's traced, and this one will vanish too. This vanishes. Okay, that's right. And I trade this guy, so I get a plus. So it is the trace here is the same, the factor of 2 vanishes, and I end up with this. Okay. And this answer is, if you want to, I could just not redo the data and do the trace. Okay, so this would be what I call here the first one. Okay. I just again broke this equation to two sides separately. And now comes the second point. We're going to look again at the conservation of the null appearance, which we found to be this was just the internal part. Okay. And here comes the solution for this tau. Okay. The solution to what? Say if you compare this to this, basically. What I'm solving is I'm trying to read this guy off this guy. Okay? Reading the trace, of course. So the all indices matches. And it is a bit more involved, it's not as direct here because this will determine the trace. Okay? This will determine tau, mu, lambda. But what we actually need is the full tensor. Okay? So it is a bit more involved, and the solution And you see why I don't want to do this too explicit, because it's big. The solution is this D is the dimensionality of space. Space plus time dimensions. Where this F should obey this equation. Okay, let me just, for convenience, call this, let me call it delta number. This should be obey this equation. So, I mean, good to see already this is solving the problem I'm offering, but you can see this a bit more involved. The point is, okay, we have this condition, okay? This is like an if you want. And the point is, okay, when, a bit more concretely, when can I do this? When I'm able to do this successfully or not? And the answer is whenever I can write this, maybe I should call it.
So, wait, what is the lambda doesn't make sense about the delta?
No, I just defined this guy.
Ah,
Okay, delta, no, it's just contamination. And the delta is this. For sure. I should have called it V because it is what I'm gonna say now. It is a virial. People usually call it, so I should have called it V, but it's too late now. Okay. We're able to do this when this virial here is a total divergence. Okay? Meaning it is something like this. It is not a total divergence. Divergence of some other two tensor. Okay. This is two. I'm gonna give some examples. Okay, but it has been proved. I guess it's a paper by Siedem Coleman, Jack and I guess Callan.
so you say this is necessary and
Yeah. The solution is this. Okay, and I'm able to do this whenever this virial here that I call delta inside of V
what is it
can be written as a divergence.
if and only if or only if or
This way.
like
Yeah, this way for sure.
this is
If
necessary.
you compute this, you compute. I'm gonna give you examples. You're gonna be able. Give me a Lagrange and I can compute this. Okay.
Yeah.
And if I can write this result as a divergence of some tensor, two tensor, then I am able to successfully improve the energy.
So this is sufficient.
Yes,
Yeah.
yes, yes.
This helps create
At least sufficient.
This is necessary.
Is it necessary?
it is necessary. Well,
Insufficient.
okay.
That's it.
I won't say this is necessary because I sincerely don't know, but see, this is the how do you say it? This is the usual way people try to improve. Okay, they go through this stage. I don't think there is any other way. So I would say it is necessary and sufficient. It is sufficient, for sure. I believe it is necessary and sufficient. Okay. So this has been a bit too abstract here. When I give some examples, it's going to become a bit won't be so complicated. But you can see that this is something we can compute. Okay. Give me a Lagrange and I can compute this. Give me a Lagrange for some field and I can compute that side. Okay. For the purpose, even if I don't know the scaling dimension of the field, it's a strongly coupled field or something like that. This doesn't matter for this problem because it's just a constant. Okay, so we can just put it inside the derivative. Doesn't matter. Okay. So this is
So in the solution, this V doesn't enter.
this V.
This V in the solution, is
solution
not present in the solution. Or this V is something related
Well,
to
if
this.
you try to do some reverse engineering here, like okay, take this guy and put it here, maybe you can
Okay.
find some condition. Yeah, but then it is a sufficient condition,
So
and
at the end,
that's-
what you want is the F. The F is the tensor that you sum to,
yeah,
to
either,
C.
I want either this F or this top. Okay.
But that F has nothing to do, or is it?
Yeah, no, that F. No.
It's another F. Okay.
So let me just.
Okay.
No, let's cover F.
Okay.
Sorry. I should have called something.
Not just so verify.
There are one paper that when they originally studied this improvement of the energy momentum tensor to make it traceless, not only symmetric, was this paper I was talking about. It was a paper by Jakiv, Sidney and I guess Cal from the 80s. Okay? It is a big paper. This is not the only content of the paper. It's actually just a side note of the paper. You can say, okay, we did this and we have this consequence, can be used for something else, maybe. So you see. So you can basically read that section separately for the whole body of the text. And there is another review. There is a 90-page review that goes to more the mathematical aspects of this improvement process, but the first 2 or 3 sections are more along these lines. I can send that to you, but I just forgot the name. It's something like currents in classical field theory. I know the title is something like a fresh look into an old problem or something like this. Okay, the first sections are along these lines, but they actually that's where I got the solution from. They don't do explicit computation. Maybe in an appendix, but I haven't read it. But then it starts to talk about Python and goes to a more geometrical approach to this. Okay, but I can send it to you later. So let me just, I don't know if I wrote it here, but it could be useful. The general solution, or say the general test to know if you can improve your tensor from a conserved tensor to a symmetric and traceless tensor is that I'm gonna erase this. If you only have a canonical energy momentum that is only conserved but not symmetric, nor it is traceless, then how it would be this time, the view. The view is something like okay, and we would have okay. Yeah, sorry. It's like this. Okay, so this is the general view. If you only have a conserved canonical energy momentum tensor and you want to improve it just in one go to make it symmetric and traceless. Okay. So the solution is again something like this. If you were able to write this, okay, not the solution. So it should be something even bigger than this. But the condition that tells you if you will be able to do this or not is that if you can write this view again as a divergence of some two tensor. Okay? And again, this is something you can compute, even a Lagrangian, some fields. Okay? Even if you don't, I mean, even if you do not know the scaling dimensions. Okay? The spin matrix you do know. If you know the field, you know the spin matrices. Okay? So this is the view for if you want to simultaneously improve it to be symmetric and traceless. Okay, it's just the sum of both figures. If you want. This is just the view is basically the internal contribution. There are those from the space-time transformation. Okay, it's basically that. So if there are no questions, I'm gonna. Scala fields. Cool.
The index is kind of
Which index?
the whole.
Okay. Yeah. It should be. Any more questions? No, you can, I don't know, you look like you have a question.
No, just someone now. Okay, no.
Wait, I haven't gone through the steps and the sum.
Yeah.
What I have is, what I have shown you is, okay, you want to do this, you need this guy, okay? This guy is this.
Yeah.
Just to make it traceless. If you want to make it traceless and symmetric, you want to do something even bigger.
Yeah.
Okay. Though I should have written it here. Something like even in LaTeX it's like 2 lines
Yeah.
worth of definitions and things like that. And okay, this is a solution. And what tells you if you're gonna be able to do this or not is this condition. Okay, in general, this condition for both traceless and symmetric. Okay. And to illustrate it a little bit, I was gonna do a Scala field example. Okay.
This condition must be connected, you said, to the fact if the tensor is traceless, then scaling symmetry implies conformal symmetry.
Yeah, but at least at the classical level, and
Yes, so this is a condition of the existence of this divergence.
Yes.
Is intimately connected.
yeah, because okay, there is it gives will give a nice overview. Remember that this is analysis that comes only from scaling, okay? And our scaling current was not traceless, okay? Because of this guy here. And then you want to ask the question: can I make it traceless, just like I made the energy momentum tensor symmetric or rotational symmetry? And the question can be either yes or no. It will be yes if you can do this, it will be no if you cannot do this. Okay? And if the answer is yes and you can improve, the solution is this. Okay? And the first side, this will just be okay, I can make my energy momentum tensor traceless. But as we discussed previously, this also implies, it's like a gift, this will also imply that scaling symmetry will imply the full conformal symmetry.
This is
Okay.
like the point.
The classical form. Okay.
That's like what I was. So I'm not sure if I missed something, because in the end you use only scaling invariance to show then that you have the full conformal invariance. That's like what I don't
Okay,
really get, because the arguments all based on this.
Yeah, basically this. Okay.
But like all arguments that we present there, like okay, you want to have tracelessness, blah blah blah, and then you look for a solution. This only uses in the end
Scaling.
scaling invariance.
And the point is, you can maybe face this like that. Okay, we haven't discussed the special performance transformations here.
Exactly. You would
And
expect this to enter.
you can face this. The answer to this question: can I make my image momentum tensor traceless only from only with scaling symmetry? And you can face this lesson like, yes, I can, if my theory also has special conformal transformation, and no, I cannot if it doesn't have it. Okay. Though you're not using any explicit, you're not using the special conformal transformations to study this question. Okay.
So,
So this is a test.
So maybe the invariance under the special conformal transformation allows you to write your delta lambda as that gradient. Could be related to the
Yeah, sure.
fact that you
Sure,
can
yeah.
do this, right?
Yeah, I told you that would give you the special conformal current, conserved current, and it is how do we call it? The conserved current would be just remember that the special conformal transformations have one vector index, 2. Okay, so the current will be a true tensor, just like translation work. And if a radical minus sign here or something like that, but you should have this one. You can see more or less it is basically when you did I'm just not sure how the indices match here. That's what I'm not recalling. But when you did the special conformal transformation, they have something like this. Again, plus and minus, I don't remember. If this is plus, then this is going to be minus. Okay, we have this form here. And where B was the parameter, okay, just like A or omega or lambda. Okay, and you can see just basically this structure here times the canonical energy momentum tensor. But I'm just not sure how the indices contract with each other. It has this form, just like basically the scaling.
One use a trace, and then you have a delta mu.
Yeah, I don't think that it is the trace that you're saying this.
Yeah.
I don't think it is this.
Okay.
I don't think it is this.
Okay.
I guess something like this maybe, and then the would be here, but then well, this would have to be. It's something like that, and while it does follow, then you can ask the thing we were doing at the beginning of the lecture. What does the conservation of this current implies? And you see that it implies that it's traceless. Basically. Because it is conserved, when you hit the equal tensor, it's going to vanish because it is conserved by translation symmetry and all that. And then in the end, you only end up with a trace term. And since it is conserved, it's going to be equal to 0. Okay? So, you can again face this problem here that we discussed as okay, I want to check if my theory is invariant in the full conformal group, but without using the special conformal transformation because it can get messy. Okay? Maybe because it is a non-linear transformation. Okay, it goes with x squared. Alright. So the solution to this problem is this one. Okay. Yes, I can do this. If I can write this zero as a divergence. Or not, if I cannot do this if I cannot do that. Okay. I cannot write it as a divergence. Okay. That's one way to understand this lesson. I want to see if my theory is invariant under the full conformal group without using the full conformal group in the analysis. Okay? Because this case, you can easily check if your action is invariant under scaling. Just rescale things. Pretty much like you do when doing renormalization group, something like that. Okay? But special conformal transformation is not that straightforward. That's why this discussion is relevant. Okay? Do we have time for examples? I won't be able to do everything I planned. There is only one example here, maybe two. There is a Scala field example, and I could also discuss a Maxwell example. Or I can discuss the word identities, which is okay. I would just state basically the word identities, or if you want to derive the word identities, then specialize. And the word identities will be the quantum statement. This, so which you prefer? I won't have time for both, probably. No, we won't have like 20 minutes. Examples?
Yeah.
Okay.
I mean, the other thing you will do the next lecture.
Yeah, I can do the next lecture. But I don't know. I don't know what else I would do. Maybe it'll be like a half an hour lecture. I don't know. Okay, so let's do. Can I erase this? Yeah. So, now the problem is, we're gonna take some theory with an action, and we want to find out if this theory has conformal symmetry. There are two things we must do first. There are two things we must do. The first is to ensure it has scaling symmetry. Okay. This seems obvious because from our discussion. The point is, if you try to apply the second step without ensuring that you're doing this for a scaling, a theory that is the scaling environment, then you're going to run into some kind of environments for scaling. So it's just to talk about that. Always take your action, do some rescalings, and see if it is invariant. Okay? If it is, then you do the second thing, which is mainly this. So you compute this virial and you see if you can write it as a divergence. Okay? Some two tests. And the example I'm going to take is let's just right. Let me just take a free massless Scala field. Okay? Let's compute the since it's going to understand this. The animal method tensor is basically this. You can compute this either by Miller's theorem, and since this is Scala field, you don't it will be symmetric because you won't have spin matrices here. Okay, so for the Scala field, this is going to be symmetric, even if you do this by Miller's theorem for translations. Or alternatively, you could couple to gravity, apply some disturbance to the metric, and read off the response as anyone does. Okay. And let's see if it is traceless. Okay, this should be the first step. Okay, take a theory, compute the energy moment tensor, and see if it is traceless. If it is traceless, then okay, it is conformally invariant, at least classically. Okay. And when you compute this trace, since we're on D, space dimension, we're going to obtain a D over 2 here. And this term will be equal to this one, and with the p factor of 1 minus d over 2. Okay? And we see that this is for d equals 2. We have conformal invariance. Okay, free Scala field and 2 two space-time dimensions is conformal. The question is, for d different than 2, can we improve the this simply the camera? Okay, so this is the question we asked. If we're not sitting at 2 dimensions, can we include the name of the tensor and prove that the theory is conformal? The scalar field, the master scalar field, the master's free scalar field is conformal in n dimensions. So we're gonna do this new thing. Okay, just if you take the action. We'd have this is the first point. We'd have a lambda t here, okay, from the measure. Okay, I'm taking x to lambda x. Okay. So I get a lambda t from the action, from the measure of the action. I get a lambda minus 2 from the derivatives, and this is a free theory, so the scalar dimension of the scalar field is equal to its mass dimension. So basically, I have 2 minus, which is d minus 2 over 2. Sorry. So, but we have 2 scalar fields, so yeah. Okay. And I guess this is the other way around. Okay. This is the momentum space, so in confirmation space.
Yeah.
Right? It's okay? I'm rescaling I'm rescaling space, okay, real space. What I looked in here previously was the mass dimension, which is 1 over the space dimension. Okay, so it is minus d plus 2. So you see, this all cancels. Okay, so the action has scaling symmetry. And now the question is, we need to compute this zero with this part only again because this guy vanishes because it's a scalar field, and we have to see if we can write the result in this form. Okay.
Just a moment.
What?
The memory is gone.
The what?
They have 1 minute.
How long?
The memory.
Oh, okay. So here's a point. I'm gonna give you the answer. Okay, the answer is that this guy is the scaling dimension of which I guess something like this. Okay. We can't write this as a total divergence. So it is the answer. It is conformal in any dimension. Okay, the mass is free. Scalar field is conformal in any dimension. You know, let's just compute it. Okay, so this the mu here is. Is it done?
Maybe.
Okay, so our field is just scalar field. Yeah. And then, the experience rate for this. Taking this derivative here, we only end up with something like this. Okay. The factor of 2 goes away because I have 2.